this diagram, okay, so this graph actually represents the black body very well. So while this sphere is a hollow sphere has a small cavity here. So any incident light through this cavity will 100% will be 100% observed. Okay, we just go into this hollow, isn't it? So there is no scattering, there is no reflection. 100% of the incident light will just enter this cavity. In other words, 100% of the light will be observed. Okay, so now this black body, okay, through this absorption, yeah, gets hot. Okay, so what would happen if it gets hot? All right, it now have lots of the thermal energy, isn't it? And then this thermal energy will vibrate these atoms, okay, vibrate the atoms of this black body. And then we have this atomic vibration, all right, which will now generate the radiation, electromagnetic radiation. In other words, it's the light, okay? Light is radiated from this black body. And then that radiation is also pictured, okay? The light coming out from this cavity, so there won't be any loss of the radiation, right? So from this, we roughly understand what is black body. And then, well, we already know that this black body radiation is temperature dependent. Okay, it's temperature dependent. So when you look at this graph, our x-axis is the wavelength and our y-axis is the intensity. Okay, the light intensity, and then depending on your temperature, okay, depending on the temperature of the black body, their radiation pattern is actually shaped differently. Okay, so 4,000 kelvins will follow this big radiation, and then 3,000 kelvin will follow this pattern of this shape of the intensity. All right. So when the scientists try to model this black body radiation, and then when Stefan Boltzmann actually discovered this important relation, the intensity, okay, intensity of this radiation at any given temperature, okay, intensity of at any given temperature is actually proportional to the temperature of tau of 4. Okay, so this is very sensitive. So even we have a small change in the temperature, small change in the temperature is going to be amplified. Okay, because we have the power over 4. So small change of temperature will amplify and intensity. So that's why we use this the Stefan Boltzmann's law to make this the thermometer. Okay, because the small change in the temperature will just amplify the intensity. Then Wien's displacement law also states that the wavelength maximum times the temperature is always constant. Okay, it's always constant. So if I use this diagram again, so let's have a look at this 4,000 Kelvin, okay, 4,000 Kelvin, and then we want to find this wavelength maximum. Right? So wavelength maximum can be the wavelength at the peak intensity or the wavelength in the longest wavelength in the curve. So which one are you going to choose? For your lambda maximum, are you going to choose this peak intensity or the longest wavelength? What would be more sensible choice? Peak or longest wavelength? It's going to be the peak wavelength, okay? Peak wavelength. Because your wavelength times temperature must be constant. Okay, wavelength times the temperature must be constant. So if we are going to choose the longest wavelength, well, most likely the longest wavelength, actually, we are going to have the longest wavelength from different temperatures actually is nearly the same, isn't it? So this Wien's displacement law cannot be satisfied. So our wavelength maximum is the peak intensity wavelength, okay? Peak intensity wavelength. So, well, we apply this BN's displacement law for this 4000 Kelvin, and then you see that our maximum wavelength is around here for 4000 Kelvin, alright? Now, let's also try to apply this BN's displacement for the 3000 Kelvin, so I'm going to use different color. Then for the 4000 Kelvin, our maximum wavelength is here, somewhere here, okay? So it should be here. So then you see that for higher temperature, maximum wavelength is shorter, and then for lower temperature, the maximum wavelength is longer. That's why, that's how this BH displacement law can be satisfied, okay? Then, although those two discoveries are very, very good, still those two, those two discoveries or the laws cannot explain, alright, cannot explain this shape itself, cannot predict the shape. Alright, so that's how the Planck actually come up with another model, okay, that precisely predict this shape. Alright, so the Planck's law use this spectral intensity, alright, the spectral intensity. As you can see here, this spectral intensity at a given temperature, okay, at a given temperature. So let's fix it 4000 Kelvin, okay, at a given temperature. This intensity will follow this wavelength dependence. Okay, this wavelength dependence. And then we have the exponential term to predict this exponential decrease. Alright? So then one thing you may want to be careful is this. So Stefan Boltzmann's law relates the intensity, okay, relates the intensity and the temperature, intensity to the temperature. Alright, then this intensity, as you know, the unit is watt per meter square. Okay, power over area. And then when we come to this Planck's law, the spectral intensity, okay, the spectral intensity has a unit of watt per meter cube. Okay, in order to have the intensity, you must multiply this into wavelength. Then we will have the usual intensity. Okay, so the spectral intensity does not give you directly the intensity, alright? You must multiply this spectral intensity into the wavelength. Then you will have the intensity. Alright? So when Planck come up with this model, he actually assumed a couple of things. So the first assumption is this atomic oscillation, okay, or atomic vibration that generates the radiation is discrete. Okay, so the blackbody radiation first comes from the atomic oscillation, and then this atomic oscillation is discrete. Okay, this is discrete, it's not continuous. Alright, so because of that region, let's say that, well, we already know that from Planck's this model, our energy, okay, the light energy or radiation energy is h times the frequency, and then we know that this is frequency, and then h is the Planck's constant, yeah? And then this equation is true for one photon, okay, one photon, alright? And then if we consider a power from torch or power from the laser, you must multiply into the total number of photons. Alright, then we will have the total energy, okay, from the light source. Alright? So let's assume that our frequency is very high. Our frequency is very high. Then what will happen to the energy? So frequency is high, therefore our energy is going to be high too, yeah? Our energy is going to be high too. So then this, according to the Planck's model assumption, this high energy is originated from this discrete energy levels. So when the electron jump up to the excited level through this thermal absorption, okay, thermal energy, it will decay to this ground level, and then from this radiation, the light will be emitted, and then this is going to be here. Alright, so this energy is going to be large. However, this energy gap is too big. So in order to have this big jumping, the probability is low. Okay, the probability is low. So total and so the probability is low. Therefore, when you consider this energy and the probability, the total power or total intensity from this big energy gap is going to be small. Okay, so total power or total intensity is going to be somewhere small. Alright? And then let's now consider a longer frequency as low frequency, okay, low frequency, so longer wavelength. So F is now small, then correspondingly its energy gap is also small. Okay, so our energy gap is now small. Okay, our energy gaps are now small, so the electrons can jump up to the upper level easily, and then when they drop to the next intermediate level, it will generate this HF low frequency or H over wavelength, longer wavelength. So energy gap is small, okay. Therefore, the generated the radiation energy is small, but probability is large. So, its total effect is moderate intensity. Okay, moderate intensity from the black body. Therefore, when you look at this diagram, when the wavelength is low, okay, so I'm going to look at this post-starting table. When the wavelength is, the frequency is low, in other words, wavelength is longer, so they have longer wavelength, okay. Although probability is good, so we are going to have a lot of transition, but because of the energy gap is low, so we will expect some small intensity coming out from the black body. And then when we move to shorter wavelengths, when the frequency is very high, then energy gap is very big, isn't it? So therefore, the probability to have that transition is also moderate. Okay, so we have only this much of the intensity. And then there is some optimum value. Okay, optimum value where you can expect the biggest or the largest intensity. Okay, so this is all about this Planck's law that dictates this model, this black body radiation. And then one important assumption is this: the energy is discrete, and that this becomes one of the foundations of the quantum physics. So now let's move on to the second topic, which is the photoelectric effect. And then I know that there is very nice demonstration in your lecture video. Okay, so please watch the lecture video, alright? If you haven't done so, but because my emphasis is going to be more toward this tutorial course, so I will just copy that demonstration diagram here, alright? So let's assume that we have a metal plate, alright, two metal plates, and then we put the ampere meter, and then we also put some the potential, and then photons are actually incident on this metal plate. So let's say there is incident photon. So if the photon carries the energy with HF over Hg over lambda, isn't it? So this energy of this photon, okay, is strong enough to kick out the electrons from the vector. So electrons will be ejected from the vector. Alright, and then those released electrons can travel towards the other vector, which is now activate this, not activate, which can be measured from this ampere meter, isn't it? So then I want to draw a diagram. Okay, with external, okay, potential versus current. Alright, and then now we yet consider this external potential, we just will measure this current, okay, under this irradiation. Then we have some charges released from this metal, and then those charges can travel to the other plate, isn't it? Therefore, even without the external potential, we should be able to read some ampere, some current, yeah? So, well, without external potential, we will have some current, isn't it? So, we will have some current. Now let's apply this potential, and then, well, for first instance, well, I'm going to say this is, let's say, well, the forward, okay, forward bias. Then we then apply negative minus potential on this rising plate and the positive potential. Then this negative potential definitely will push, okay, push away this electron. Therefore, our current is going to be larger, isn't it? Because this will push this electron. So our current will be larger. Alright? And then I keep increasing this external potential, and then it happened that this current somehow saturated. Why should this happen? Why the current does not increase linearly? Why the current is saturated, must be saturated? Because your electrons, okay, where those electrons come from? From the photon, isn't it? Photon incident on the metal and then kick out the electron. So photon kick out the electron, alright? So this current is going to be ultimately, okay, maximum current is ultimately determined by the number of photons, okay, number of photons. So I put 10 photons, then there will be 10 electrons released. Okay, so 10 photons will kick out 10 electrons. So I have just a certain limited number of charges, therefore my current cannot increase linearly all the way. Okay, it must be saturated. Okay, determined by the number of photons. Alright? Now I then reverse the bias. Okay, so now we with this potential arrangement, then of course the electron and the potential, they will attract each other. So this potential will hold this electron, can hold this electron. Therefore, well, by increasing this negative or reverse bias, then my current is going to be reduced. And then at some point, there won't be any more current flowing. Okay, and then we call it stopping potential. Makes sense, yeah? This is the stopping potential. Alright? And then, now, so okay, because I already defined this stopping potential, so then this is this stopping potential. From this stopping potential, I can define this potential energy. My potential energy is going to be stopping potential times its charge. So this is the electron charge, isn't it? So I have this stopping potential, or the potential energy that related to this stopping potential. And then this potential energy is going to be the maximum potential energy for this electron, isn't it? Because with this potential energy, the electron cannot move, so there is no kinetic energy. Does it make sense? Alright, so with this potential energy, there is no movement of the electron, therefore this is the maximum potential energy. In other words, because of the energy conservation, this is going to be maximum kinetic energy of the electron. Okay, so this is going to be the maximum kinetic energy of the electron. Alright, because of the energy conservation. Alright, now I finish one set of experiment, and then I will move on to the next experiment, and then where I want to increase the intensity now. So I want to increase the intensity. Okay, I want to increase the intensity. Then from this equation, then you will see that there are two ways. Okay, two ways to increase the intensity. The first way is you can increase this frequency. Okay, if you increase the frequency, your energy goes up, so which means your intensity goes up. Yeah, we also know that this relation, yeah, energy is power and then your power is intensity times area. Yeah. So energy, power, intensity, they are all linearly connected. Yeah. So if I want to increase the intensity, well then I can actually simply increase the frequency. However, I don't want to change my light source. I want to keep my light source the same. But yeah, here I want to increase the intensity. How can I do that? So with the same frequency, I can still increase the intensity. Yeah? How can you do that? You just increase the power, isn't it? You just increase the power. So in the quantum physics, when you increase the power, what does it mean? In the quantum physics, I just increase the power. Yeah, 1 watt later, now I increase to 10 watts later. Okay, what actually happened? So what does it mean in quantum physics? I increase the number of photons. Okay, I increase the number of photons. Alright. So another way to increase the intensity is I simply increase the number of photons. Okay. So previously I just keep 10 photons. Okay, instead of the plate. Now I just crank it up to 100 photons now. Okay, so now let's consider I increase the photon numbers, so it will increase the intensity, right there. Because I increase the number of photons, so what would happen to the number of electrons? Okay, so when 10 photons release 10 electrons, now 100 photons, so how many electrons will be released? 100, yeah, very good, 100. So in other words, our intensity, our current is going to be higher. Our current is higher, isn't it? And then I'm going to increase this, I now apply this external potential. Therefore, this external potential will push, okay, will push this electron, so it will contribute to this increase of the current. And then this will be saturated. Because ultimately, the current is determined by the number of photons. Okay, number of photons. So we have just 100 photons, so there will be only 100 charges. Okay, so this is the saturated current is already used up. Okay, is 100 electrons. Now I apply the reverse bias and then increase this potential onto this direction. Then as you know, the current will reduce. And then one striking thing is that it will stop at exactly the same stopping potential. Okay, so although I increase the intensity or I increase the number of photons, the stopping potential is the same. Okay, and then from this we can conclude one thing: this stopping potential is going to be the material property. Okay, as long as I keep the same metal plate, then I will have the same stopping potential. Okay, actually, at the fixed with the frequency. Alright? So then I want to make another problem. So I just explained to you that intensity, okay, intensity can be changed by changing the number of photons, but it can also, we can also adjust the intensity by changing the frequency. Yeah? So I just want to now explore that relation, yeah? How the frequency actually affect or contribute to this total electric effect. In order to do that, I will draw a graph. So this x-axis is going to be our frequency, and then our y-axis is now going to be the maximum energy of the electron. And then we know that this Kmax is actually potential frequency times its charge. Okay, or I will also sometimes write it as E because this charge is electron charge, right? Then, so I change the light source, okay? Now I change the light source from, let's say, the blue color to the ultraviolet color. So then when I start from some frequency somewhere here, and then at this frequency there is no photoelectric effect because my kinetic energy is 0. Okay, and then I increase the frequency, then it turns out that my kinetic energy of the electron actually increase linearly. Okay, and then just related to this, the photon, the frequency. All right. And then, well, I will also see that, well, this is a linear curve, so then I can actually extend it to the y-axis. So we have this intersection point. Okay, so this intersection point, I will say that this is a phi. I will introduce this later, right? Then, because there is a linear relationship between Kmax and the frequency, so I can write one equation as this is going to be h. This makes sense, yeah? Because this is linear relation, and then we have this Planck constant. And then, if you have a good eye, then you already know that this is actually photon energy, isn't it? So this is photon energy. So this photoelectric effect now states that the photon energy is directly related to the electron energy. Okay, directly related to the electron energy. Now, because this curve does not starting from the origin. Okay, we don't have this relation unfortunately, but we have to introduce the intersection point. So we are going to put this minus pi to complete this equation. Yeah, and then this is called the work function. So why do we need the work function? So when the photon, bombards this metal, okay, it must break this bond. So electrons is bonding to this metal. Okay, so the photon must first break this bond. So this work function is the potential energy or this attach or bond energy of the electron to the metal, and then our photon energy first break this bond, and then the rest of the energy is going to be converted to the electron energy. Okay, so photon energy is going to be the electron energy plus this bond energy. Alright? So then now we have this equation, alright? Then well, this point, okay, this frequency where it actually starts or initiates the photoelectric effect looks very interesting point. So that's why we put place more emphasis on this point of the frequency. And then because this frequency actually tells us whether we have this photoelectric effect or not, so we call this cut-off frequency. Cut-off frequency. Okay, so higher frequency than this cut-off frequency, we are going to have the photoelectric effect, but frequency lower than this cut-off frequency, there won't be any photoelectric effect. Okay, so in order to have the photoelectric effect, the frequency must be larger than this. Then, well, I want to make this the mathematical expression for this cut-off frequency. So I know that K max equals HF minus pi, and then our cut-off frequency now becomes cut-off frequency. Okay, and what is our kinetic energy at the cut-off frequency? What's kinetic energy for the cut-off frequency? And what's the kinetic energy at the cut-off frequency from this diagram? Zero, yeah? Your cut-off frequency, your K max is zero, isn't it? So this is now zero. Then my cut-off frequency is going to be the work function divided by h, and then you know that this cut-off frequency is converted to the wavelength, cut-off wavelength. Therefore, your cut-off wavelength is going to be c times h over the work function. So you can calculate the cut-off frequency as well as the cut-off wavelength. So if you are given any metal, then by measuring this current, you should be able to, well, decide this cut-off frequency. Okay? And then which is going to be your cut-off wavelength. So I just explained about this graph, okay? And then also what the relation between the maximum kinetic energy and then the potential energy. And then when we make a plot with frequency and then maximum kinetic energy, then we now found this relation, and then at the cutoff, okay, at the cutoff, because this kinetic energy So I have a small question for you. So let's have a look. So well, this is our photoelectric effect graph, and then frequency now increase. Okay, frequency is increased. Then what will happen to this stopping potential? Now we increase the frequency. Then what will happen? So well, it's going to remain the fixed or move to the right, move to the left. So what would be what do your thought? Yeah, well, let's vote, yeah? What, A, B, C, yeah? So please don't choose D, right? So A, B, C. Wow, you can be wrong here, yeah? So, what do you think?
B.
B, okay, we have one suggestion, B. Any other thought? Uh-huh. I will wait for one more vote. A. So we have A as well. Alright, so the correct answer is actually C. So why? What do you mean by this increased frequency? Our frequency now much higher, okay? It's very high frequency. In other words, your photon energy is also high. Okay? So your photon now become more energetic photon. Alright? So when this energetic photon kick out the electron, then your electron is going to be more energetic too. So it actually has more kinetic energy. Therefore, to stop your energetic electron, you must apply much larger potential. Isn't it? Therefore, this will move to the left. Alright? Or you can also use your equation. So K max, your kinetic energy of the electron is hf minus 1. Okay, and then this is also related to your potential energy. And frequency now goes up, which means your kinetic energy goes up. Correspondingly, your potential energy goes up. Therefore, our stopping energy will move to the left. Alright? Now, I have one more question. So, we now consider the second graph. Now, we increase the intensity, but then frequency is fixed. So in other words, we just increase the total photon numbers. Okay, we just crank up the power. Then what will happen to this cutoff frequency? This cutoff frequency. It's going to be fixed or to the right, to the left. So we just increase the power, okay? We fix these light source and then we just increase the power. Then what will happen to this cutoff frequency? So let's vote again. So A, B, C. Yeah, can be wrong. It says no harm, yeah? So it's better to be wrong and then correct it now than you make a mistake in the exam. So yeah, well, what's your suggestion? A, B, C? C, okay. Any other suggestion? So I will wait for one more vote. A, alright. So very good. So the correct answer is A.
Yes.
Okay? So frequency, when you increase the frequency, okay, when you increase the frequency, alright, then this kinetic energy, so the electron gets more energetic. Alright, so we understand that part, but it does not going to have any contribution to the cutoff frequency. Alright, once the photoelectric effect is initiated, alright, after that there is only the more energetic electron that just comes out, kicked out. Okay, so it does not change the keyhole. So it doesn't change this cutoff frequency. Cutoff frequency will remain the same. If you want to change the cutoff frequency, the only way is to change the material. Okay, you can change the material to make some change in your cutoff frequency. Okay, in other words, your cutoff frequency is going to be material property as well as your these work functions, also your material property. All right. So then, I copy those these slides from your lecture note. So I just so that I just want to show that we are on the same page. Okay, we are on the same page. Alright. So these are the lecture note. You can actually download from the course website. So this have you. Now let's start the tutorial question.